तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the previous lecture, you got some idea about the control, that is specifically I said data path control. Now, in this lecture we will take a look at the data path architecture. Now, let us go back a little and then see that at the highest level we have what is called, let us say the user point of view, the program, okay, and then this goes through many levels, that is we talk about codes and so on, and at the lowest level we have the state information, that is in each state there is a small activity which we had identified as the register transfer level activity. Okay. So, while discussing this RTL activity, we saw that the sequence in which the register transfer actions must take place will be decided by the controller or the control signals, and the activity itself we saw that consists of moving the data around some specified paths and controlling this. Okay. So, gave you some idea about these control aspects in the previous lecture. Now, we will take a look at the data path part of it, for which we will assume a typical architecture. I hope you would recall we said earlier that architecture is different from organization. Now, that is not precisely what we are talking about here. Okay. Now, here basically it means how you can put the various components together so that whenever the processor needs, the controller will issue the appropriate signals so that the physical connections will be enabled so that the data will move around. Okay. Now, we will see more of it. As I said, so we must have some idea about the components involved in it. Now, some of what we knew already or had seen, first I said ALU or the arithmetic logic unit, which forms core of the processor, right. Then while talking about the processor, as said, we also came across this component, that is the CPU consisting of registers. We saw some of these registers earlier. Basically, it is the one which holds information, okay, that is on the CPU side. Now, we will see some more components, after which I will discuss a typical data path architecture. Okay. Now, today I will introduce one more thing. We will see more about ALU. Before that, I will talk about one component which would be used in the architectural, okay, for the data path, that is the called multiplexer. What exactly is a multiplexer? Just sometimes simply referred to as a mux. Essentially, it has multiple inputs which are called data inputs, okay, more than one, it can be many. Now, these are called the data inputs, and depending upon another set of inputs called control inputs one of these whatever is there will be output. Okay. So, the output of a mux is one of the data inputs. Now, which one, that will be decided by the control input. Now, you can see a parallel to what we are talking about earlier. We are talking about the path over which the data will move, and that particular path will be decided by a set of control signals. Now, in fact, you can see the summary of it even in this single component, that multiplexer. So, multiplexer is one we will use. For instance, if the multiplexer has two inputs, I will be using a diagrammatic representation like this, which that is a mux. It has two inputs called as A and B. Sometimes we refer to this as A leg of the multiplexer and B leg of the multiplexer. Now, one of these will be output. Now, which one will be decided by a control input? Okay. It is easy to visualize. Now, you can have more than one, in which appropriately we must have the set of control signals which identify uniquely which one. That is what it is, right. Now, similarly, let us take a look at this ALU we have been talking about earlier. Now, ALU is the arithmetic logic unit, that is a unit which is capable of performing a set of arithmetic functions and a set of logic functions. I will assume for our purpose that it is an ALU which is capable of performing, let us say, 16 arithmetic functions, okay, capable of taking, we will talk about a set of data, and then it will be carrying out some function. So, 16 arithmetic function and let us say 16 logic functions. That is, the ALU is capable of executing 32 different functions. All right. Now, we have to assume a few other things, like what is the data size of the ALU that it goes. Now, we will assume again an ALU which accepts two sets of inputs, and what is the size of the data. In this particular one I was just mentioning data input, we are not talking about the size. Now, in the case of ALU we have to talk about that too, because one of the arithmetic functions can be addition. When we talk about addition, then we have to indicate whether it is a 4-bit addition, 8-bit addition. No? So, that 4-bit or 8-bit actually refers to the size of the data. Now, suppose this were a 4-bit ALU, then precisely what we mean is the data input which come on the A leg is going to be 4-bit size, 4-bit wide. Similarly, the one on the B will also be 4-bit wide. If it were an 8-bit ALU, then we will be having an 8-bit input or A input or an 8-bit B input, that is what it is. Now, that apart, there can be more than 4-bit output. Certainly, if it is a sum, let us say, there is a possibility that addition of two 4-bit numbers will result in a 5-bit number, right. So, generally what we say is a 4-bit sum and then an extra 1-bit carry, right. All right, we will not bother about that because we are not talking only about addition here. Now, how these 32 arithmetic or logic functions will be indicated? They will be indicated using the set of control inputs, okay, which go to this. So, because we have 32 functions, okay, total, if we have a code, then a binary code, let us say, then we need a 5-bit code, mainly because a code which indicates which of the functions, mainly because 2 to the power 5 would correspond to 32. So, a 5-bit code will uniquely represent, right, will uniquely represent, for instance, code say such as this may represent one function, another code Okay, orbital, I will just put something, will represent specifically another of this function, and so on so forth. And so with a 5-bit code, you can have as many as 32 combinations, and that code uniquely will identify what exactly is to be done. For instance, this may be a code, let us say, for one of the arithmetic functions, let us say add. Okay, and say this possibly may be a code which represents one of the logic functions. We have not talked about logic things. So some logic function, okay, I will possibly give some idea about these logic things later on, okay, some of these. And sometimes you may have even a code for a simple thing like passing on just the data A onto the output. Now I will just call this as the output of ALU, name it as out. Okay, in which case, given two sets of data A and B, I am just assuming there is some function which simply passes on onto the output leg the one which is on the A. Now there may be another code for this. Now let us just say this is the code for that, and so on and so forth. Like this, you can go on defining different functions. So ALU, which is the heart of it, will be getting because it has 32 functions, will be getting a 5-bit code which will uniquely identify what this particular one is going to do. Similarly, the mux should have a control signal which will pass on A or B, just that. Now mux only passes on the data, whereas this ALU will be doing some, carrying out some function, arithmetic or logic, can also pass on, as in this case. Is also one of the functions. It simply passes on, right? Okay, now that's about that. Now with these functions, let us try to develop the data path architecture. We have to start with the ALU as the core. Now, having seen ALU as the core and then the function of the multiplexers and registers, now we will try to put them together and develop what I will call as a typical data path architecture. Okay, it is typical in the sense there is nothing very sacred about this. Just something with which we can carry on our discussion about data path. That's what it is. What did we see earlier? We had some registers, for instance, okay, an instruction register. I'll just call it as I register. Then we are talking about an address register, remember? So that address register, I'll just call it as A register. Then we had we were mentioning about data registers, so I'll just assume that we have say 2 data registers. Okay, so for this I call this as D1 register, or just one of the 2 data registers. I'll assume another data register, let's say D2 register, and then I was previously telling, that is in the previous lecture I was talking about the address being placed on the contents, and then I was trying to tell you that since the program is actually executed instruction after instruction, there will be one register which works more as a counter, and then the name of that particular one is a program counter, right? That is, program counter usually holds the address of the instruction. So we'll call that as just PC. Okay. Now, address of an instruction to be fetched will normally be available in the PC. This will be passed on to the address bus, and then at the bus level, essentially we have the address register interfacing with the address bus part of it, or just call it as A bus. Let's not worry about what the width of that particular one is. Okay. It's meaningful if this is a 16-bit bus, then it's meaningful to have a 16-bit register. This part of it we have discussed earlier. Okay. Now, the ALU will subsequently be involved in carrying out some processing on the two data, but then subsequently we have to possibly also pass the program counter contents to the A register. So, the path for that also must be created. So, what I would do here is introduce one multiplexer, okay, introduce one multiplexer, if necessary we will name it later. So, either the content of this or the program counter content will be passed on to this ALU, right. Then in case of arithmetic or logic processing, the D2 register contents will go over the B leg, and I will assume here the other data A is available from D1 register, alright. Then I am trying to keep the number of components as low as possible. Now, the ALU output, let me say it goes through another multiplexer, okay, another multiplexer. Why should we assume a multiplexer here? We will see that sometimes the processed data may be passed directly over the data bus or the D bus, okay. Specifically it is the output part of the D bus or the data bus, and there is also the input part of the data bus, that is the data may come in. So, this is also in fact part of the D bus. So, you can see that data sometimes the CPU will place on the bus, and sometimes the data will be accepted by the CPU. So, when accepted by CPU, the data will be coming over this. When the CPU places the data, it will be going over that, right. So, for instance, in the case of memory read, the CPU reads from the memory. So, the memory will place on this and the CPU will accept and rotate internally. When the CPU writes into the memory, the CPU will send the data over this. So, that is the arrangement there. And for simplification, I will just assume the data that comes over this gets routed to any of these registers like this. Of course, one can go on making more complex diagram than what is shown here. Now, for the purpose of our discussion, I will just assume this is the data path architecture. Now, what is this? For instance, when the CPU places address, now shall we go back to that state after state information. In T1, we are saying the CPU places the address on the bus. So, in other words, A bus, okay. Onto the A bus, address part of the bus, the CPU places address. We were in fact discussing instruction fetch, remember, in which case the instruction, since the instruction will be pointed to by the program counter contents, essentially in T1 it is the program counter contents which will be placed on the A bus. Now, for this architecture, what exactly it means is this: a path must be set so that the program counter contents will be placed over the A bus, and this in fact is the path, okay. And then it is placed over the A bus. This is the path. So, now if this path is set up during T1, then the goal is achieved. The contents of PC, what is the content of PC? It is the address of an instruction to be fetched, which is available here. This must be routed through this multiplexer passed on to the B leg of the ALU, and the output of ALU must be passed on through the mux to the A register, which must be enabled so that the whatever is there in A register is passed on or placed over the A bus. So essentially you can see ultimately the contents of PC, which is again a register or counter, whatever you call, will be transferred to A register, and that is made available on the address bus. This is precisely the data path that must be set up during T1. Okay. Now normally we say since a program is executed instruction after instruction, we would expect after this is done the PC contents to pass on to the next location. So that is the next step that must be done. All right. We didn't discuss that when we were discussing the previous thing earlier. Then I think we said during T2 the CPU puts a read control signal. Now it's not really that is shown, it can be shown here. I'll just write down nevertheless the read control, because we have not shown where exactly is the control part of the bus here, so we will not bother about that. So the controller must place the read signal on the control bus. Now that must be done. Fine, that is during T2. Then in T3, assuming the memory responds immediately, the memory is going to do this. CPU is not again involved. We set the data from the memory, so which I will call as memory data. Okay, the data from the memory is placed on the data part of the bus. Essentially, the memory will respond and put it on this. That's what it means. Now again CPU comes into the picture and it moves whatever is there on the data bus. Okay, since we started saying the data that is fetched is an instruction, it must get routed to the instruction register. Okay, this is what we discussed in detail in the previous lecture. Good. Here, after program counter contents are placed on the address bus for which specifically the data path is shown, when during T2 the CPU is placing the control signal, read control signal, because it has to fetch, the CPU must read in, right. At that particular instant, for instance, we can see that the program counter contents are incremented, so that next time, that is in the next machine cycle if necessary, the program counter can point to the next, say, byte or address location. It means basically these both these signals can be done in parallel.
PC plus 1 to PC.
PC contents, oh yeah, you are right. PC, sorry, the contents of PC must be incremented and placed in PC. That's what it is, right. The contents of PC must be incremented and the new value must go into PC. That's what it is, right. Correct. That's a thing. Good. Now let's say this. Let's just take this data path which has been done, that is in T1. Now I hope it's clear. In each state, the data path such as this must be set up. Similarly, in the case of other states also, right? Now for T1 it has been shown. In the case of other states also, similar thing must be done. Now let us see here. What is this multiplexer's role? The multiplexer essentially passes on whatever is there on this leg or on this leg onto the output. So the control signal here must be given so that shall I again call it as A or B? Either the one that comes on A, what can come on A? Just the one data register contents can come on A. Either this or this must be passed on, right? So the control signal here must be such that B gets passed on to the output during T1. All right. Suppose I'll just assume that on to the output either this or this is always passed on. Then it's enough if I have only one control signal. Now depending on whether it is 0 or 1, right, either if it is 0, let us say A is passed on, if it's 1, B is passed on to the output. So this in fact is the control signal, whereas this is the data signal, this is the control signal. Now similarly here ALU, we will assume the same old 32 function ALU, in which case there will be 5 control inputs, right, 5 control inputs. So a 5-bit code basically, that's what you have, right. So I'll just call this particular code as say some C0, C1, C2, C3, C4, that's a 5-bit code. So one particular code which says the output of ALU will be what is placed on B, that particular code must be here, in which case the output will assume the B input. Okay, that code must be generated during T1. Now similarly here too, I'll just assume a 0 or 1, a simple signal. So why not I call this particular signal as M0, okay, which may be 0 or 1. I'll call this as M1, this particular signal 0 or 1. And what should be this? I said one code. So some code you just assume, let's say if this were say 0 0 1 0 1, that particular code implies that, okay, this is the code which says that out of ALU, okay, onto the output of ALU the B contents will be placed, okay. So this particular code must be there. So some code, good. And what else? Yes, what about the registers? What about the registers now? We have two things. One is the input for the register and the other is the output. So we must have control signals enabling the input side as well as enabling the output side, okay. The way I have drawn this particular figure, it may appear as if something is enters and travels down the register as in the case of shift register. So it's not so really. What I mean here is if a 4-bit or an 8-bit code comes, it's going to be passed, okay, in parallel, okay, right. So don't get mixed up with this. Good. So some control signal which will enable the in or out of these various signals. Now during T1 we have to see that this out signal is enabled for the PC register, so that this out signal will enable the contents of PC passed on over the B leg input of the mux. Similarly during T1 we have to see that this must be input must be enabled of the A register. Similarly output of the A register also must be enabled so that it will go on to this, right. So in other words we need to set this in and out of A registers enable so that the information can go through. Okay, sometimes it may be done in 2 steps. Good. So now just the information that the program counter must be passed on to the A bus, and one state T1, that's the register transfer activity, means generating the out PC out signal and setting M0 say 1 so that this B information can go on to the output, and generating a code, whatever be the code, doesn't matter, so that the appropriate code for implementing this function, for passing the B input onto the output and enabling this mux so that this information and not this is passed on to this, okay. And finally the particular, that is, the program counter contents go over this path, and finally it must reach a register. So this control signal must be enabled, and then this also must be enabled so that it is placed on the A bus. So now you can see that the architecture which we have assumed talks about a collection of components, say registers, multiplexers and ALU in this case, and the data path is set up essentially because of the generation of the necessary control signals. Now these control signals, when generated and given to the respective components at a given instant, that is the state duration T1, will achieve transfer of PC contents onto a bus. Now this is one step. So like this, in each state the control signal must be set, which will set the data path, okay. So on, so forth, we can go on now. Now we'll, like this we can go on discussing for each of these. For instance, yeah, I will go to the last state T4, let us say. That is, by this time what is it we have assumed? We have assumed that memory has placed the data on the bus and it is available on the input part of the data bus, and it must get routed to the instruction register. So the data path for that would be enabling so that the data coming over this gets routed to this, and finally it must reach the instruction register. Now once the CPU gets the instruction, then depending on what that instruction is, it will start generating the necessary signals for further implementation of that specific instruction. Because you remember I was telling that any instruction, okay, the instruction, the format is a set, instruction format is a set, it's going to consist of essentially two things. One part of it is the opcode, which tells what the instruction is. The other part of it is giving some information about the operand. Now how many operands and how these operands can be referred to, they will all depend on what exactly is the instruction it must carry out, okay. Now once the instruction is fetched into the instruction register, then the CPU proceeds, and the instruction may be just say 1 byte or 2 bytes or 3 bytes. Now suppose we have a 3 byte instruction, and if the data path width is only 1 byte, so as I mentioned earlier, that instruction must come in 3 steps, which means 3 machine cycles, okay. Once the entire instruction comes in here, right, then it can proceed. Well, it all depends, but the very first byte which comes into the instruction register itself will give some information to the processor. So once the instruction is fetched into the processor, now this will be given, I will write it here. So once the instruction comes into the instruction register, okay, this information will actually go to the, in fact it's a multi-bit instruction. This will go to the controller, okay, because what is our basic cycle? Fetch the instruction, decode or interpret the instruction, and then execute, Okay. So, the instruction register must go to the controller, which actually will include the appropriate decoding part of it, that is I will call it as instruction decoder. Okay. So, this must be part of it, and once the instruction is decoded, then the controller will generate the necessary signals once again to make sure that the different data paths are set up for that particular instruction. Get it? Good. So, essentially the architecture is going to help define the data path, and the set of instructions, each, as I said the previous lecture, each instruction must be analyzed, right, to create all these low level activities. So, they would tell what is the sequence in which the control signals must be generated. Okay. So, the instruction register will get the instruction, so it will be decoded, and essentially that will be the information to the controller, so that the subsequent data path setting up and the sequence of control signals that must be generated, they will all be decided subsequently. Now, let us get back to the original data path discussion, that is just for one state, that is in which the PC contents are placed on A bus, we said this is the data path, and the path is specifically set up mainly because the controller is generating these various signals. Now, let us go into detail and work out. That is, in this particular mux, the M1 must be specifically, let us say 1, so that this is passed on to that, and ALU must be set in a specific operation mode, so that the code, let us say C0 to C4 is, say, this one. This is very arbitrarily done, that is 0 0 1 0 1, assuming that is the code which helps basically the contents placed on the B input, B leg of the ALU input, to be routed to the output. Okay. So, that we get this over here, and then this particular mux M0 again, let us say, is set to 1, so that this information goes there, and to see that the PC contents are placed on the B leg of this mux, this in output, okay, output of the PC must be enabled, and then so going back, so going forward, the output is enabled so that it comes here, and this is 1 so that this comes and not the other one, similarly and so on. Now, this comes, that is the PC contents get routed over this, and it must enter only the A register. So, this input, okay, must be enabled, this is another control signal, and since this must go on to the A bus, also the output of this register must be enabled. Now, we have other control signals also, that is in and out of I register, like this in and out of all these registers, specifically only out of PC and in and out of A register must be enabled during T1, then we get this. Similarly, these things we have seen in detail. Now, let us work it out. I'd say if we have this code, that is I register has in and out signal, okay, and so on. Then we have the A register. Similarly, for that also we have in and out. Then we have the D1 register, same in and out. Then we have the D2 register, again in and out. then we have the PC, again in and out. Then we have, did we call anything specifically here? No. We'll call this mux 0 and that as mux 1. So we have mux 0 that's only one particular one. Then we have mux 1. Then we have the ALU, which is a 5-bit code. Okay. Let's say that's the 5-bit code. So this is only one bit here, and then a 5-bit code. Now, to see that this data path is set up during T1, essentially we start with this. PC out, that must be 1. Then mux 0, that must be 1. Then ALU, we have just arbitrarily assumed a code, that is 0, 0, 1, 0, 1. Then mux 1 again is 1, and then A register both in and out must be 1. Now rest of them set them as 0. Now we have a specific code, right? This specific code, when generated by the controller, will set this data path. So the controller must generate this signal, this particular code during T1. That's precisely what it is, right? Now, what is the say the architecture of the controller? Now, let us see whether we can extend further. Now, since you know that during T1 this is the code must be generated, similarly for T2 we can arrive at another code, T3 another code, T4 another code, just for one machine cycle. Then for each of the instructions you have many machine cycles. For each of those machine cycles we will arrive at the same thing. So put them all together. Then we would have got the codes that are needed for executing all the instructions of the CPU. So assuming that you put all these codes in memory, okay, some memory will put it. We will put all these codes in the memory and so on. Now from the memory, if you just anytime read only one of these codes, that is in our case let us say this location contains T1, this location contains T2 and so on and so forth, like this for all the instructions. And anytime if you just read only one of these words, then in that particular, which we may call it as remember what I was calling each one of these as one small step, right? Each one of these is one small step, that's a micro step, because an instruction is executed using these micro steps. And so each of these is also called a micro instruction, right? Now we are seeing specifically the micro instruction is nothing but something which sets the data path. That's what we are finding it, right? Now for each instruction the set of micro instructions must be executed. And now we see also that each micro instruction specifically is going to set the data path and tell what the CPU must do in that particular state. Take any state, that particular state. So that is one. So generally this one is called, since memory consists of words of some, okay, with, now here we are only talking about this data path control signal. Now this particular word is essentially for the data path control. So it's essentially a control word, and since it is one small step giving the micro instruction, generally we call this as one micro word. It's one micro word, it's in the memory, and when you read one into a register like this, generally this will be called a micro word register. Okay, micro word register. Good. Recall our discussions on memory earlier. Said memory usually is organized so that we talk about each location, and each location has a unique address, is it not? Now we find that if we talk about address of this, which say contains this code, essentially that address is nothing but the state number itself. That is, given a machine state, given a machine cycle, a specific state in that machine cycle is unanimous with this particular address also. So if we have a, say, a decoder, right, which generates a specific unique address, so this particular decoder will take in some address, whatever be the size, okay, let's not worry about some address. That address must uniquely generate the code, and the data contents from that memory will be read into it. Then we would be having the data path control signal for that particular state. Now we said the CPU is essentially a state machine. It goes through state after state. So at any time only one state, right? Which means during that particular state, the information needed for setting the data path is made available, right? Now it so happens what you are seeing here is only the control signal, and this entire thing is to be used for setting the control part only, being that, right? So to this memory word we have to add other things so that we can really sequence through these various things, right? Good. So we just put it as what we have is the data path control word. Okay, that's what it is, data path control word, and that is essentially is the output of the controller in setting the data path. Just that's what we have here. Okay, so we can allocate one location for T1, in another word we can accommodate the control signal code for T2, and so on so forth. But then how to sequence through these, that's another step. For a study of that sequencing, you have to recall what we discussed in the previous lecture. That is, we were discussing in fact T1 in terms of some state code T1, T2, T3, T4, remember, recall. So T1, during T1 the output actually that is generated will be this particular code, that is actually the output, which enables the PC contents go on the data, PC contents getting routed through A register actually to the A bus, address bus, okay, that this we saw in the previous lecture. And also we introduce a ready input signal. That means the sequencing is associated with given a state, what is the output that is to be generated so that the data path may be set up, and also what is the next state it must go to, and in some state there may be occasions when some input also must be checked. For instance, in T2 we were seeing in the previous lecture that a ready input must be checked by the CPU. Depending on that, the next state will depend. Okay? That is given, for instance, if T2 is the present state, depending on the ready being 0 or 1, the next state will be, say, in this particular, as per this ASM chart, the next state will be T2 itself, or it will be T3. Okay? This sequencing information must also be included in the memory. That is, this particular micro word will not only consist of whatever has been shown there, which essentially is controller output. So I would say this in the controller output signal, which will be used for setting the data path. It must also say what is the next state and what are the inputs to be tested in each state. Okay? Now what exactly is this? This is for a given state. Now we think we set for T1, state T1, okay, which corresponds to the state code T1 here in this chart. Now we must also have information about what is the next state. Okay? It so happens for T1 the next state is T2, but in the case of T2 it depends on an input. It may be T2 or it may be T3. And then another one is, in a given state, what are the inputs to be checked here? That is generally called inputs to be tested, or say we will just call that as test. So a micro word in a memory which describes the control sequence will not only have this, which is only the output part of it, but it must also give the sequencing information, that is giving the next state for a given state. What exactly is this word? This word is for a given state, no? So given a state, what are the inputs to be tested? That information must be there. Then depending on the condition of this, what is the next state, and then also it must give this particular one. Now this must be worked out for each state for all the machine cycles, which means for all the instructions. So the CPU design, as I was mentioning in the previous lecture, starts with getting the instruction set, that is sometimes we use this word instruction repertoire. Okay, that's nothing but the set of instructions for a CPU. Then each instruction will be worked out having the necessary machine cycles. How many machine cycles? It all depends upon the type of the instruction, okay, the width of the instruction. As I was already mentioning, if an instruction word is 3 bytes, for fetching the instruction itself you need 3 machine cycles, and then you have the execution part also, and then each machine cycle consists of specific states, and in one state one low level activity, a register transfer level activity takes place, and what we have here is for one such activity for which the data path will be set up. Good. Now for a given state T1, this word will give information on what are the signals that must be generated and what are the inputs that must be tested for that given state. For instance, here in T1 there is nothing to be tested, fine. In T2 we will see that ready is an input which must be tested, that information will be here. Okay. Then it also says depending on the condition of that, it says what must be the next state. For instance, in the case of this T2 state, the next state is T2 or T3 depending on that particular input. So there are essentially 3 fields of the micro word. One is the output field and one is the next field and another is the test field. The test field essentially is telling what are the inputs to be tested for that given state. Okay. So, once we have this information and put in the memory the entire thing, then the whole behavior of the state machine is there in that memory in terms of these microwords, for which the starting point is what are the instructions to be tested. And what is it we have assumed here? We have started our discussion with an assumed architecture. Right? There are different reasons based on which this architecture will be developed. We have not really gone into them. So, we have only taken this architecture as a starting point and then discussed how these various things get related to.